Hi everyone. In this video we're going to be adding displacement vectors in 2 dimensions. So we're making a vector diagram where we have a number of displacement vectors. In this particular example I've got 5 displacement vectors that I'm going to be putting together. Jackie wandered around the basketball courts at lunch. Her movements are listed below. Find her displacement after she stopped moving. Now, as we put all these vectors together, as we put all these displacements together to find her final location, to find her resultant displacement, her final displacement, we need to remember to have an orientation, a scale, draw in the vectors accurately, and then find our resultant vector. First of all, we need our orientation. So we'll draw the orientation in. We're going to say that this way is north. And we're going to say that we've got the east-west dimension on there as well. We don't always put this in, but I think it's useful to put it in this time because a number of our vectors are north, south, east or west, so it helps us to remember which way is which. We need a scale, and I think a useful scale for this one is going to be 1 centimetre equals 10 metres. Okay. Let's track Jackie's movements. Initially, her first movement is to walk 30 metres north. At 1 centimetre equals 10 metres, 30 metres must be 3 centimetres. So we find our first vector like so, and we draw that one in. Our vector is pointing upwards. By the orientation, that tells me that that is north. I put in my second vector, so Jackie moves 30 metres north. She then moves 50 metres to the east. So this second vector, the tail of this second vector is going to touch the head of the first vector. So we're going to go 50 metres to the east. We draw that vector in. This is our second vector. And we're saying here we are at 50 metres to the east. Jackie then goes 50 metres south. Again, the tail of this third vector goes to the head of the second vector. And we move 50 metres south. Our fourth vector, we're going to go 20 metres west. 20 metres at 1 centimetre equals 10 metres. 20 metres can be covered by 2 centimetres. So we draw that one in, and there's our fourth vector. And once again we're going tail, head, tail, head, tail, head, tail, head. Our fifth vector is 20 metres north. 20 metres north. Our resultant vector, our final vector, will now be drawn in, and we draw our resultant vector. The tail of the resultant vector begins with the tail of our first vector. The head of the resultant vector goes to the head of our final vector. So we draw that in. Here's our resultant vector. Now you'll notice conveniently that my resultant vector here is on the horizontal. It is on the east-west axis, which means that I really don't have to worry too much about diagonals. I don't have to do any calculations, but I don't have to do any calculations anyway because I've got a scale and I've drawn all of my vectors to scale. So what I can do to find my resultant vector is I can say, fantastic, my resultant vector equals, and I take my ruler and I measure it, and I see there it's 3 centimetres and it's pointing to the east. So the resultant vector is 3 centimetres. If 1 centimetre is 10 metres, then 3 centimetres equals 30 metres. And that is to the east, my resultant vector. Now, the actual distance travelled by Jackie, the distance travelled by Jackie is not 30 metres at all. Distance is a scalar. So we've got 30 plus 50 is 80, plus another 50 is 120. 80 plus 50 is 130. Plus 20 is 150, 170 metres. That's her distance. Magnitude, no direction. But her resultant displacement is a vector which is equal to 30 metres east. 30 metres east.